So now we have made the concrete, we have designed the structures. All we expect is how long it's going to last. That's the question comes to our mind. This is a brief outline of my presentation, some introduction, impact of ignoring durability, how do we define a durability, and what are the different factors that can influence durability, and then something related to the durability issues and a summary. First of all, when we design a structure, so far, how do we design it? We design it taking the tensile strength, compressive strength, inflexor. We provide the reinforcement detailing. For durability, what we do is we simply provide a cover, right? Under the prescriptive guidelines, we have the water to cement ratio, minimum water to cement ratio, or maximum water to cement ratio, which we can go to, how much cement content we have to add, and finally, a cover varying from 25 to 75 mm depending on the exposure class, severe, extreme, and we feel we are safe. Is it adequate enough, or do we have to consider durability in a more specific way than just prescribing? Because nowadays, earlier it was just OPC, but now after every few years, we are able to find more and more new SCMs. Do all these SCMs need to follow those guidelines, or do we have to something better to assess these and change these durability requirements? Now, what happens with when we don't take care of durability? These are some of the pictures that I have collected, some from online and some from my own experience in the industry, or say when I go with professor to the sites. You can see most of them structures are failing to be serviceable. These are some more pictures. These are from the recent the Professor Bishnoi do when he go to the site visits on Delhi NCR. You see the lots of buildings, lots of cracks, some even toppled. So these are the issues that we face. Now, do we take care of these issues at the design stage? Probably not. We need to consider that. Now, a quick survey. How many of us do actually believe that concrete durability is a property of it? I want the professors to sit out of it, less the students. How many think it's a property of concrete? Just raise your hands. Nobody thinks it's a property of a concrete? You. So there are quite a few who thinks that durability is actually a property of concrete. Surprisingly, it's not. It is not a property of concrete. It's an ability we provide to the structure. We design it to be durable. Durability is depending upon the type of material and the type of environment we are subjecting it to. So we have to design a material to be durable into a certain environment. And how do we design it? We design it by taking proper conceptual planning, selection of the materials, sound construction practices, maintenance of the structure timely, and all this knowing what will the environment it will be that we are going to subject the structure to. Now, how do we actually define durability? So far, it's an abstract kind of word, just like my friends talked about compressive strength, M25. When I say M25, I know what M25 means. It's 25 megapascal of a strength. And we are able to achieve it, then we say, yeah, that's the strength. But what about durability? Are we able to do the same thing with durability? Can we label something as durable and subject it to a different environment and expect it to be durable again? No, we can't do that. So how do we define a durability is, although over the years the view keeps on changing, so I'm trying to introduce with a relatively new view of durability. So maybe if you have read in the literature, you might be familiar with a different definition of durability. So just bear with me, this is a new one. So it's the ability of a structure to withstand the design environment over the design life without undue loss of serviceability or need for a major repair in it. Maintenance doesn't mean that you have to do a large scale repair of the structure. It means minimal cracks or something that a local damage you can repair with. It's not about that you completely scrap the structures and repair it and now you say, see, it's serviceable again and look, it's having a durability. No, you can't do that. It should have a limited type of failures, fixtures, cracks, not a complete deterioration of the structures. If we are going for a major repair, then surely your structure is not serviceable. Now, what are the common factors that influence durability? Just like I said, it's an ability that we provide depending on the environment. So how do we provide ability? As a designer, we are flexible with the materials part. Environment is not in our control, so we decide it depending on the environment. So this is a twin-fold kind of thing where two different things influence the property or say durability, its ability. So one side is material properties, that's what aggregate to binder ratio, water to cement ratio, what is the porosity of the structure, what is air content, what is the quality of your concrete, and other side there are environmental factors. These environmental factors include temperature, moisture. These two things vary everywhere. You must be feeling, you came to Delhi, all of you from different places, you must have felt the change in the moisture and temperature, all of you. So those are the two things. Another interesting things are your groundwater composition, especially in case of Delhi. In Delhi, in many regions, this groundwater has chlorides, which can be very deteriorating for your structure. Another things that are is your maintenance and your other ions in the soil or the seawater or the carbon dioxide level in the environment. Now, thing with durability is, unlike compressive strength, we decide for 28 days. Durability is not something that you can decide within a month or 90 days. It's design life. And can we wait for a design life to test something like cast concrete today and we will see for 50 years, can we use the same mixed design for casting the structure or not? No, we can't. We have to pre-assess, will it be able to last for next 50 years or not within the time frame of maximum to maximum 90 days. So how do we do that? To do or to assess this, we majorly focus on certain tests. Some are accelerating tests, some are not accelerated but more of property or material specific. Say porosity and pore size distribution. This one I would say is the one factors that you would see in every durability issue talked about this. Because in concrete, all the transport happens through this only, porosity and your pore size distribution. And we talk about durability is majorly the ingress of the species that are outside the concrete to the inside of the concrete. So this is the one factor that I would say you have to think about a lot when you are talking about durability. Now there are other tests, water absorption, how much water your concrete is able to absorb. That gives you an idea if, say, it's subjected to a dry environment, how much moisture will it take? With moisture, there will be lots of things that will be going inside. So, depending on your wetting and drying cycle, you can decide how much it will take every time it goes inside. Next is the gas permeability. One of my colleagues asked about carbonation. Carbonation is a gaseous phase. So, it will get into through the concrete with the voids that are air. So, again, a permeability property of such kind of things can be assessed by gas permeability, but I will explain more in detail afterwards that how it can be sometimes misleading also to us if we just focus on one test and ignore the other tests. Some of the tests others are resistivity. Often we have concept that if we have a high resistivity, our concrete is more durable. We have this notion. Secondly, the tests are rapid chloride penetration test or rapid chloride migration test. These are the two tests generally we use for. First is rapid chloride permeability test. This is the one test we oftenly use for the quality control. Not much in India, but surely in other countries we do use it. And the next is for the chloride environment, chloride migration coefficients. As chloride ingress takes place over the years, generally in environment there is a less concentration of chlorides. What we do is we provide a potential and we monitor the ingress of the chlorides under this potential field. And within the relatively short time of maximum to maximum 4 days, we are able to assess how the structure or what will be the chloride depth in the structure for so many years, after so many years, say 50 years, 30 years, 40 years. Now, just again quick voting. So how many of you thinks the major I guess you would know, it's what's the major durability cause as per you guys? Somebody can speak, no issues. What? How much do you think corrosion would be issue? 10%, 20, 30, 40? How much of the cases? Just a ratio.
Depends upon your environmental conditions.
No, I'm saying throughout the world, if there are different issues, what is the maximum or major issue that's happening? How much fraction of the total cause of deteriorations will corrosion be? 10% issues will be of corrosion, 20% or more than that?
More than 10%.
More than 10, 20, more than 30? Surprisingly, you are well aware, but then again, it's more than even 50%. So you see, most of our issues are of corrosion only. Most of them. The cause of this corrosion can be different, be it admixed chlorides, be it chlorides coming from the outside, or be it carbonation, or be it may a macro cell of some kind. But the cause is different, but more than 50% is corrosion. Now, there are other ones. If you can guess some, what are the other durability causes that you can think of?
Chloride attack. Chloride.
Comes into the corrosion.
Sulfate.
Sulfate attack. What more? ASR. Abrasion. Freeze and thawing. Generally, we in India we don't hear much about freeze and thawing. Especially we all are living much below in the states where we don't see much of a snow. So we don't see, and where we have snow, oftenly we have a construction of wooden or something. So whenever we go there, we are not able to perceive it. Then again, ASR, alkali silica reactions. Then there is sulfate attack, chemical type of attack. Then there is other plastic settlement, crack, other creep and thermal shrinkage cracks type of issues. So we have a huge variety of durability issues, which we need to take care at different stages. And sometimes it's like, after you assess, you can sometimes take precaution course to strengthen your durability life or your structure serviceability limit as well. Now, I will be talking about few of them, not all of them. So if you have any queries about the rest of them, just contact me. I will try to brief a few about other courses as well. So before I get into each, since we are about a workshop of Lc3, and I told you pore size and pore distribution is the one thing that influences everything, I want to let you know pore size distribution and porosity of a Lc3 system. If you assess Lc3 system porosity by water absorption or say even MIP, and you just look at the final value, you would generally see that you are getting a high value compared to OPC. So that's even case with most of the blended systems. If you take it, you do a MIP or water absorptions, you are probably going to have a higher porosity than OPC. But does its porosity alone that decides the transport or the damage or the ingress of the species? Most of us think yes. To be honest, I was the one who was thinking that. So, not a big thing. It happens. We feel that it's the porosity that's decided, but it's not actually the porosity. It's more of the pore size distribution, interconnectedness of these pores, the surface charges of pores, the fractal dimensions. There are lots of other things. Now, the interesting things comes here is, in case of blended systems, say PPC or Lc3, compared to OPC, your pore size distribution is way different than OPC. In OPC, you have coarser pores from 100 nanometer to 1 micrometer, a huge dimension of these pores. Major chunk lies in that. But when you come to Lc3 kind of system, you see the most of the pores are 100 to 10 to 100 nanometers. And the chances of these low size pores being not connected is much more than the maximum size of pores being not connected. So we have to take care, when we talk about durability or something, that we don't just take one property and rely on it. We rather get into 2 or 3 properties to properly characterize our material when we say if it's durable or not. It's not just one property we get into, it's giving me high resistivity, it's durable for everything. No, it's not like that. If giving me high porosity, it's not durable. No, it's not like that. When you do these kind of things, it's better when you do with the same kind of composition. If you're looking at OPC and you're looking at OPC at 0.4, 0.5, 0.6, then it's well good. You can compare it freely because whatever is there in porosity will be reflected in the pore size distribution also, because the blend composition is same. But when you change the composition, would the things remain the same? No, it doesn't. So when you are talking about the different blends, I would rather say look at more than just singularly focusing on one property. Then, because this one property can be misleading for you. Now let's see this effect of this different pore refinement in case of how it happens. and how it influences other properties. One of the quick method is absorption. Water absorption rate and water absorption are two different things. Rate gives you idea about what is the rate of ingress. Water absorption gives you about the total volume it gets absorbed in. It gives idea about porosity, and this one gives about the rate of the ingress of the moisture or say water into the concrete. If you will see here, you see that compared to the blended systems, compared to the OPC, the blended systems always try to have a lower, especially the blended system at 0.5, the one with the slags, composite cements, and the Lc3. They give a much lower initial sorptivity and much lower secondary sorptivity at both the water to cement ratios. To compile, this is a compiled literature from Dandapani et al. From 2023. It's a Rylam paper about the review of the durability issues with the calcine clays, and you can see that when we consider different metakaolin blends, or say individually calcine clay or a combination of calcine clay and limestone, we always end up with the lower sorption compared to the OPC system. That's because we are defining the pores. Our pore size distribution is changing. The porosity may be higher, but our refinement is so good that the increase of the water itself is getting reduced down. Now, knowing these things, let's start to get into the actual durability issues that we voted about, the corrosion and chlorides or ASR. So I will be talking about corrosion in RC structures, and the major two causes for the corrosion in RC structures is carbonation and chlorides. So we'll talk about those two. Then we will talk about alkali-silica reactions, and then we will talk about sulfate attack also. So if you have any queries other than these, just let me know afterwards. I will just talk with you. So when we talk about corrosion, like one of my friends just right now said that, okay, chlorides. When we say durability issue, it's not corrosion. Sometimes we think chlorides and corrosion are different. The thing is, in terms of the corrosion, what we do is we decide the total life into the two stages. One is the initiation stage, another is the propagation stage. Your initiation stage is the part where the chlorides or say carbon dioxide that ingresses into the structures and lead to the active corrosion. The point where the rebar starts to actively corrode. Now, this point of actively corrosion, reason for this active corrosion can be different fluorides from the reason for the carbon dioxide. I will talk in detail about that afterwards. So once this active corrosion starts, what happens is your rust starts forming. Once this rust starts forming, it starts building, and the rust is having a much more volume compared to the parent metal iron. It can be from 2 to 6 times more than the iron itself. Now you can think, like, if I have a hole of this size or something and try to squeeze something more into this, it will start to burst. That's what we say the crack starts to develop. The cracks are starting to form. Now these cracks will just go, and it will start from inside near the rebar, and it will eventually appear on the surface. Your crack will reach to the surface. Now, after this crack reaches to the surface, the paths that were initially through the concretes now can be direct through the crack itself. So your rate of deterioration will suddenly jump up. And maybe depending on your design criteria or a designer's view, this acceptable limit damage can be here, here, here. Generally, we kind of right now think of it as here. We don't want the corrosion to even initiate. That's how we consider for acceptable damage. But then we are ignoring the life of the propagation phase itself. But we need to know, can we consider this? Because sometimes this can be a huge chunk of our life. When you are talking about a structure, this can compose a significant portion, maybe 10 to 20 years. Nobody would want to destroy their structures 20 years before. So we have to assess this propagation phase as well. Now let's see what corrosion is. Corrosion is an electrochemical reactions where you form anodes and you form cathode on the same rebar, on a different rebar, depending on your distribution of rebars. It can be either. Now, in any type of cell where anode is a cathode, you will see a connection would be made with, outside we made with a bias where we monitor it, but inside also there is a solution which provides the connection for the ions to travel. In case of our concrete, this connection is provided by the pore solution that exists in the pores of the concrete itself. This is the connection that works. Now, corrosion doesn't start with just chlorides reaching it. There are certain necessary conditions. When all of them are met, then only the corrosion will be there. Otherwise, it will be just waiting for the other condition to come. So, one is oxygen. You need oxygen at the level of the rebar. Another is moisture. You need pore solution. If you have water, then only you will have pore solution. So you need moisture at the level of the rebar, and you need a breakdown of the passive film. Most of you have heard about the passive film, I guess. I hope so. If you not, a just brief slide about passive film for you guys. In concrete, we have a pH more than 12. This is a Pourbaix diagram for iron. So when you increase the pH, there are different zones where iron can be stable, immune, or be corroding, or it's in a passive film stage. In a concrete, we have a pH of around 12 or greater than 12. So in this range, at this potential, you see there is a layer kind of passivity. So this is a kind of layer that forms around the rebar, gamma Fe2O3. That's a protective film which doesn't allow the rebar to corrode, specifically under these conditions. Luckily, this is the thing with our concrete. We always have it in a passive zone until unless somehow we destroy this film. Now the cause of destruction of these films leads to these kind of structures. Might be you have been seeing around, if you are in Delhi or somewhere, you might have sometimes seen a chunk of falling or rebar being visible to you somewhere. Or sometimes it can be much more drastic. You must have heard about the recent cases of the Chintal or Greenview in Gurgaon, where a complete slab fall down of a building, of a living building in a common area, the complete slabs fall down. So these are certain kind of situations when this passive film gets destroyed. You start seeing these rust marks, you start seeing these cracks, and your structure starts appear to be non-serviceable. I don't think any of you want to live in a room where you have a roof like this. I think nobody would like to do that. So, to summarize, what can be the consequence of this destruction of passive film in the corrosion? Initially, the penetration attack starts. You start to lose your rebar diameter and the rust starts to form in. The rust will lead to generation of the voluminous rust product, the loss of iron. This will start inducing tensile stress into the concrete and you will start appear to have cracks. These cracks, when you see, will start to lead into the loss of the bond that you have with your rebar of the concrete. So your distribution of the stresses which were happening through rebar to concrete due to the bond development, you start to lose on that. And when you start to lose on them, the collective effect of this and the penetration attack, the loss of the rebar, you start to lose ductility of your structures. And sometimes you see a sudden collapse of the structures. These are the critical consequences when you ignore the corrosion in a structures. Now coming to what I talked about, what are the main causes of the corrosions? Oftenly, the main causes of the corrosions that we see are the carbonation, one of the reasons, and another reason is chlorides. What happens in carbonation is atmospheric carbon dioxides get into the concrete systems and it reduces down its pH and you start to lose the passivating film. I showed you at around 12 only you have a passivating film, but once your pH starts to fall below low, you don't have that passive film anymore protecting you from corrosion. It's destroyed. While in case of chlorides, you see chlorides get into the concrete and they locally destroy the passivating film. It's not like carbonation that your whole front is moving. It's just locally at a point the passivating film is lost due to the chlorides being there. Now, the difference between in these two type corrosion starting from these two causes is, in terms of carbonation, you see a front completely and your rebar will be corroding throughout. You have lots of micro and macro cells nearby each other. But in case of chlorides, it's much more different. In chlorides, you will see that at one point the rebar is lost considerably, at other point it's not lost. But then again, it's more harming than this type of corrosion. Now let's start with the one of the process, carbonations. Like I told you, carbonation is the process where atmospheric carbon dioxide gets into the concrete through the voids that contain airs. and it mates with the water, it dissolves into the water, it forms carbonic acid. Now, concrete, I guess everybody knows concrete have calcium hydroxide, Portlandite, sodium, alkalis, Na2 equivalent. We all calculate this. All this reacts with the dissolved carbon dioxide and forms carbonates. Carbonates doesn't like to dissolve. They like to get out of the system. They start to precipitate. And their precipitation means calcium is also getting out of the system. The species like calcium, sodium, and potassium, which were causing you high pH, now started to go out of the system. You start to see your pH starts to fall. This pink color shown is a phenolphthalein indicator. When you spray a phenolphthalein indicator, when pH is greater than 10, you have a bright pink color. So you see with carbon front moving, this pink front is moving backwards and this color is, you see when it reaches to the rebar, you see the pH is less than 9. Now when pH is less than 9, you have lost your passive film, which was actually protecting you from the corrosion. Now the active corrosion will start. So carbonation. If we see different carbonation species, we see that for different blends, the carbonation rate is different. In comparison to OPC, all the blended systems will have high carbonation rate, and the carbonation rate will be higher for blended system as we talk, because the carbonation in the blended systems, the Portlandite reacts with the SCMs to form the secondary hydration products, which leads to the consumption of calcium hydroxide. And this consumption of calcium hydroxide leads to a depletion of alkalinity already in the systems, so we get a higher carbonation rate. But consequently, sometimes we can see that depending on the water to cement ratio, a common approach that we use for tackling this carbonation is we can reduce the water to cement ratio. You can see at 0.5, the carbonation depth is much higher compared to 0.5, and at 0.4, it's much lower than 0.5. So if carbonation is your major cause, what you can do is you can simply change the water to cement ratio if you are worried about the carbonation. Changing the water cement ratio will provide you enough time for the structure to passive film to get destroyed. Now I was talking about gas permeability. Gas permeability, for performing the gas permeability, what we do is we dry the concrete, and then under a pressure we observe what is the loss of the pressure of the oxygen or say any other gas, nitrogen, after certain time over the decay. It's a falling head type of a test. You see, in these type of systems, blended system which have pore refinement and which shows a nice pore refinement and which have less interconnectedness, they appear to give a very good low value of Darcy's K value. So you would think that if carbon dioxide is getting inside at the same rate, probably we are having it better in the blended systems. But does it need to be just gas permeability that's deciding it? Probably not. It's the reserve alkalinity also. The term reserve alkalinity means the buffering capacity of the system to counter the carbon dioxide increasing in the system. In case of blended systems, the total alkalinity is lower for the blended systems compared to the OPC. OPC have a quite high total alkalinity. So it's the combination of two factors. When you combine these two factors, you see a nice trend. And you can consider this. Your alkalinity combined with the pore characteristics is the one which helps you assess the carbonation coefficient of your structures. Using one factor may not be the good idea. It's better to take 2 or 3 multiple tests and combine them and see the main result. Now, before I jump into the corrosion, carbonation have a effect on the pore structure itself, because you are dissolving the calcium hydroxides into the system, and these are solid before. When they dissolve, you are precipitating calcium carbonate, which is again solid. So you are changing the pure geometry of your structures. If you see for Portland cements, it leads to a coarsening again, but for metakaolin blends, it leads to the coarsening again. So the effect of the carbonation on the type of the blend is similar to each other, be it for limestone, calcined clay cement, or be it for OPC, it's quite similar. You observe a coarsening in both kind of systems. Now coming to the carbonation induced corrosion. This is a study where they carbonated the samples made with Lc3, and they observed the corrosion rate. The corrosion rate values are in the range of 0.6 microampere per centimeter square. These are typical values that you observe when the structure is carbonating in and corrosion is there. In terms of carbonation induced corrosion, these are typical values. But when you convert these values to milliampere per year, millimeter per year, you see it's less than 0.01 millimeter per year. So you can see it's not that harmful for your structure as you be expect it to be. To elaborate it more, there is a study that compiles the literature about how at different relative humidities the corrosion rate changes. In terms, unlike chlorides where the C structure is contact with the water, we see that in the structures which are subjected to carbonation generally have a variation of the relative humidity. And at different relative humidities after carbonation, the corrosion rate can be different. The corrosion rate will be high when the relative humidity is quite high. But we all know our structures are not always wet, especially the one we are living in commonly here, are not always wet. Since they are not wet, it's subjected to your wetting and drying cycle. It's your daily and seasonal fluctuations. If you get a rain spell or if you splash some water, you see a spike in the corrosion rate, but when it's dry, it again comes down. So it's a dynamic process. It's continuously fluctuating. So often we study at extreme conditions of corrosion rate. We can't directly interpolate that into the field. We have to consider that the variation of the daily relative humidity and saturation level is going to affect our structures. Another thing is, in terms of carbonation, what's more dangerous is shallow cover depths. You don't provide adequate cover depth, which provides a quite less time of saturation. You splash it and it directly gets saturated, and you get a coarse pore structures because cover depth is less, aggregates were not able to get there. It's kind of a cement paste and finer aggregates only. So you get a coarse. These kind of situations are more critical in terms of carbonation rather than when you provide the sufficient cover depths. This is a literature study we did on a decade, like half a century old kind of a structures that is still was serviceable up to the last year. Now we demolished it because we need more space and more flats in IT Delhi. So what we did is we determined the carbonation depth for different members in the structures, and we see that the values were quite high. Looking at these values, I can say that within first 10 to 20 years, the depassivation of the rebar has occurred. But for last 30 years, the structure had been still used for beam services. Only certain regions had high corrosion rate. Rest of them were quite low. You see, micrometer per year. So only the regions which were quite moist and repeatedly being subjected to the moisture and the water observed quite a high corrosion rate values. These regions are specific. Then again, the regions where the carbonation depth was quite high, corrosion rate was not high. These are indoor environments where we live. We have a low relative humidity, so the carbonation front can move faster. But since we don't have a relative humidity there high, we don't get much of a corrosion rate. So it's not a widespread corrosion in a structure when structures get carbonated. It's more of a location specific reason. So if we consider these kind of things during the design stage itself, especially when we are being pushed toward the blended cements used because of the sustainability needs, probably we will be able to take care of the corrosion due to carbonation reason. Now coming to the chloride ingress, we see that chlorides get into the concrete from many sources. Sometimes these are admixed because of in the water or because in the aggregate, or sometimes it's penetration from the external environment, be it the contaminated soil or groundwater, or be it the sea water. And the major transport of these chlorides is advection, diffusion, and sometimes migration. These are typical chloride profiles of penetration compared with OPC and the cements blended with Lc3 having a different kaolinite content. These formulations are with 50% Lc3, like 50% clinker, remaining 50 as calcined clay, limestone, and gypsum. As you can see, compared to OPC, the initial one is quite high. That's not Lc3. That's totally Lc3 being replaced with quartz. But once you start blending the calcined clay, you start seeing that there is a decrease in the apparent diffusion coefficient. And if you compare the chloride profile after 2 years, you see that for Lc3, 79 and 50, it's much lower compared to the OPC systems. So the performance which was not as good in terms of carbonations, here it's quite different view. it's much better compared to the OPC system here. To show you more results, I would just try to show you. These are the charge transport values comparison of OPC, PPC and Lc3. You can see that Lc3 charge transport is almost in the negligible range for all the mixes compared to OPC, PPC. In fact, even at 28 days, yesterday we talked about the pore refinement in Professor Srijit's lecture, right? In Lc3, this pore refinement happens quite fast. So even at 28 days, you see the charge values are negligible. But for other cases like fly ash, after 90 days you start seeing an improvement. But then again, it's not as good as Lc3. These are some more results that I was talking about, the apparent diffusion or migration coefficient. You see, compared to OPC, the blue dots, the green dots are much lower. Even at water to binder ratio of 0.6, you have a lower migration coefficient compared to OPC at 0.4. That's how good your pore refinement is, and that's how enhanced the chloride binding is there in the systems with the blended system with calcined clays. Now coming to the chloride induced corrosion, unlike the corrosion there, chloride induced corrosion is different than the carbonation. Here no pH is effect of the concrete. Throughout the concrete, pH is not effect. Chlorides penetrate into the concrete at the same pH. They are not, but they destroy the passive film locally at one point. And anode and cathodes are formed. Anode is limited to this pit only, whereas cathode is limited to the whole rebar. So you see there is a high gap bit ratio of anode cathode area. There it was both being near to each other and widespread. Here its cathodic area is much larger than anodic area. So whatever the potential is driven by this region only. That's why we observe a more pitting like of corrosion. To be more specific, this iron, when we start dissolving, starts forming, this iron forms oxychlorides and they start hydrolyzing. In this hydrolyzing process, hydrogen is released, and locally inside the pit you start having an acidic environment. This acidic environment leads to brought down of the pH inside that pit only, not of the whole concrete but inside the pit. And if we know what is the influence of the corrosion rate on the pH, we know under the acidic conditions it's much more aggressive than the near neutral or alkaline conditions, and we get an autocatalytic process because these chlorides, they don't get consumed in this process. Because of hydrolysis they keep on getting released and they still maintain this concentration here, and we get a very aggressive kind of situation which leads to a much more drastic loss at a same point. Some of the results from this chloride induced corrosion. This is a impressed current kind of test apparatus where it used. The potential was provided and the test setup was run till you start to have a crack on the concrete surface. Or you see in Lc3, if you compare the mass loss percentage, it's much lower than the OPC and PPC. That's because you have a high resistivity in the Lc3 system. You can see at different ages or compared to OPC and PPC, your surface resistivity is quite high for Lc3 system. Even your bulk resistivity of the system is quite high. At water to dimension 0.4, you can see quite high. And again, you see these values are quite high, even the surface resistivity. This resistivity influences your corrosion rate. If you're having a high, you are probably having a better perception of going to have a lower rate of the corrosion in the structure. Now coming to the alkali silica reactions, this is a type of reaction we don't generally see very at an initial stage. Sometimes we have reactive aggregates in our concrete. Glassy content of these reactive aggregates is quite high. When they come into the contact with the pore solution, which are generally alkaline in nature, you start to form a gel kind of structures. These gels have a very affinity for water. They start absorbing water, and once they start absorbing water, they start swelling up. And because of this swell, it again starts generating pressure on the aggregates. This pressure will eventually lead to the development of the cracks into the structures, which will lead to the other ions ingress quite fast into the structures. Now, since we know this is because of the alkalinity of the system, in blended systems, we already are using this alkalinity for the secondary hydration. So we are already bringing down this alkalinity, And oftenly this alkalinity comes along with the clinker. In the SCMs, it sometimes doesn't have that high of alkalinity. Then in certain situations like this, Lc3 doesn't expand much. It's much lower than the OPC. So you are able to mitigate your ASR problem. Same, this is a test setup as per Australian standards. So there they wanted to have a concrete. They had the reactive aggregates, but they wanted to have a concrete that can pass the limit of expansion if we are going to construct anyway we using the reactive aggregates. Then when we were using 30% calcined clay, then they were able to mitigate this problem. This was the level they wanted up to expansion, the stable expansion level in the structure. But you see, OPC crosses it over this point, but in case of blended systems like Lc3, it was much lower than this. So with help of Lc3, you can mitigate alkali silica reaction. Coming to the sulfate attacks can be of two types, internal or external. Internal is from the sulfates, excess of the sulfates that are present in the concrete, and when you core the concrete at a high temperature. When you cure it at a high temperature, generally monosulfate is formed. But when you cool it down, this sulfate bound in the CSH get released, and this monosulfate gets converted into the yttringite. Yttringite, again, as explained, because of the high volume of it and needle-like structure, it start exerting pressure, and you start seeing cracks development. But external attack is when the sulfate is coming from the external source, it's ingressing from the outside. If you see, if you are subjecting the sulfates, interesting thing, yesterday's presentation, if you noticed, because we have carbonates in the system, we stabilize the yttringite, and monosulfate is no more formed. So, because of the carbonates, there is no more monosulfate in the system. So, even if sulfate comes from external, it takes the sulfate, there is no more monosulfate. So, the attack will be on the calcium hydroxide and gypsum will be formed. You don't see that kind of expansion with Lc3 and PPC system where carbonates are there. So Lc3 is able to mitigate your sulfate attack also. This kind of thing is also good in another way, like I explained, because of the pore environment and the lower sorption capacity. Even if you use different clays, since your rate of ingress is quite low, even at repeated number of cycles, you won't even have the same kind of damage that you start to appear to have in case of OPC system. Even with the systems like if for Lc3 systems, you require more number of cycles of exposure to have the same level. But now, just to summarize things, how can we decide for a structure's durability and why do we need it? When we are designing a structure to be durable, we need to design it as a designing stage only. We have to consider what to water cement ratio we are using. Do we have to provide sacrificial cover depth? What is the different exposure environment we are going to subject our structure to? We have to take care of these things and plan accordingly. We have to regularly maintain and inspect our structure. If we get a cause or deterioration, we don't have to just go and patch repair it. Sometimes there can be a different underlying cause and repairing it may not be enough. So you are just putting a facade over it, just beautifying it doesn't mean that your cause has been rectified. You have to sometimes do periodical inspection, a detailed survey of the structure to get to know what the underlying cause is so you can timely tackle it. Next, if you ensure these two things, you are ensuring your structural soundness. You are able to protect your life, human life. Another thing is, if your structures last for longer, you are going to have a relatively lower cost, because with the same cost, you are having a longer life. But if you are going to have a structure that's deteriorating, for the same cost, you can have 20 years of life or 50 of life if you take care at the designing state and regularly maintain. Finally, these solutions can be sometimes cost effective and very sustainable. These things will be talked in further lectures, how these solutions can be sustainable and how using these can bring down even the cost of your constructions also.